All right, so does anybody have any questions you would like me to go over? Go ahead.
Number 3 in the additional problems.
Number 3. So we have the length of a rectangle that's changing at a particular rate. So we're given dl dt is 2. It's maybe not the best question. It doesn't say that it's increasing, but I'm going to say it's increasing. While the width is changing in such a way that the area remains constant at 20 square centimeters. This is an important idea. And later on in the course, when we talk about max-mins, we're going to refer to this kind of equation as, and I'll write it down so you can see it. This is called an equation of constraint. A constraint is a condition that you have to follow. I always just kind of say what we're handcuffed to is the idea that whatever the length and the width are, it's always going to be 20. Always. And what we're asked is the rate of change of the perimeter when the length is 5. Holy smokes. Okay, so now we want to find dp dt. So I guess what we do here, Christian, is we start off with a formula relating the variables whose rates of change are listed, right? I mean, if we know the rate of change of L, we need an equation with an L in it to get a dl dt making its appearance once we differentiate. And if we're asked to find dp dt, then obviously we need a formula with p in it, so that when we differentiate it, we get a dp dt. But here's the issue. The issue is that when you write out your formula relating perimeter and length, it turns out there's a width involved as well. And by the way, you might read this question and see that the width is changing, right? So there is a dw dt, but even though there's a dw dt, we are not asked to find dw dt, nor do we know it. So we're not using it. And if I were to differentiate this equation right now at the bottom of the screen, I'd get a dw dt, and I'd get a dp dt, but then I would have two unknowns. So following the guidelines I've set out, we need to get rid of that w. Because I'm going to amend ever so slightly step 1. Step 1 says develop an equation that contains variables whose rates of change you know or want to know. And I'm going to amend it by saying that contains only the variables whose rates of change we know or want to know. We don't want a variable w in there because we don't know anything about it. We don't want to find anything about it. So how do we get rid of that w? Well, we can use the equation of constraint. The equation of constraint means no matter what, w will always be 20 over L. And that means I can substitute that in for w. There's another way to do it, and I've made a note to show you the other way in a second. So now my formula is P equals 2L plus 2 times 20. And knowing that I'm going to be differentiating, I'm just prepping this by saying 20L to the negative 1 so that I know how to differentiate that L. So I just want to pause there for a second. Christian, are you okay with that logic? Okay, so now what we have is perimeter equals 2L plus 40L to the negative 1, and we're off and running. So I'm finding dp dt. I'm differentiating everything with respect to t. This is equal to 2 dl dt minus 40 L to the negative 2 dl dt.
Why is it minus 40?
Pardon me?
Why is it minus 40?
Because I swing this negative 1 out in front and multiply by the 40 to get negative 40. And then it's L to the negative 2 because I have to subtract 1 from the exponent on L. And then, of course, it's times dl dt because I'm differentiating with respect to not L, but with respect to t. And I think it's the case now that we can just go ahead and put everything in. We might have a little bit of legwork to do, and it turns out we don't. We're told L. So L is 5, dl dt is 2. So dp dt at that instant in time is 2 times 2 minus 40 over 2 squared. Whoops. No. The length is 5, right? The length is 5 and dl dt is 2. Okay. So 5 is L. L to the negative 2 is 1 over 5 squared. And then dl dt is 2. Just want to run that through my head again. Yeah, I think that's fine. So what do we get? We get 4 minus 80 over 25, which is 100, which is 20 over 25, which is 4/5. Can you, somebody please run that through a calculator or your brain for me? And see if it's 0.8 or 4/5. I think it is. And if we go back to the beginning where I made the observation that I'm not told if the length is increasing or decreasing. If dl dt is positive, then you're going to get a positive dp dt. If dl dt is negative, you're going to get a negative, I'm guessing. But the amount should be the same. Because they both have a dl dt in them, right? They both have this 2 in them. Is that okay? Okay, now I want to show you a different way to do this type of question that sometimes is easier to do the different way because this becomes too complicated. And we're going to see a case like that today. So here is the problem. The problem is you want to find dp dt, but the only formula you have p in contains a w and you don't know dw dt. However, you do have a formula relating L and W. And you know what? I'm gonna rearrange this for W. It was 20L to the negative 1, right? So here's what you can do, and I'm sure many of you would come up with this idea on your own. If you differentiate this formula with respect to t, you get dp dt equals 2 dl dt plus 2 dw dt, and you're at an impasse because you don't know dw dt. How many of you see where this is going? Why don't you just differentiate this equation with respect to time? Put in your L, put in your dl dt to find your dw dt, and then put your dw dt down here. There's nothing wrong with doing that. The math is solid, right? You're not cheating, you're not using rules that you've made up. You're following the rules of differentiation in algebra. So let's see if this works. It better. So what would dw dt be at this point in time? Well, it would be negative 20 over 5 squared times the 2. And I hope you're seeing it's going to be the same. This is the same set of numbers we had in there earlier, isn't it? It's right there. Right? So now what we can do is say dp dt equals 2 times dl dt plus dw dt. That's what that works out to. And you get the same answer. So again, I like what I said there. I think it makes sense. As long as you're following proper rules of algebra and proper rules of differentiation, if what you do leads you to dp dt equals a number, then what you're doing is right. Any questions with this? Any other questions? Okay, so it turns out that a couple of the questions we're going to do today can make use of this idea of either getting rid of a variable you don't want or choosing to differentiate a second equation. So now I believe this is on page 8 and we're at example 7 now. So grain is being poured into a conical pile. There's an auger that's pulling grain out of a bin or something, and it's going onto the ground in a pile in the shape of a cone. We're all familiar with the shape of a cone. It has a circular base. It looks like that, right? It turns out that there's this set of data you can look up in many references. It's called a granular consistency. And it turns out within certain boundaries that when you dump grains, something that's granular, like salt or wheat, in a pile, it will form the shape of a cone, but based on the granular consistency, the ratio of the height to the diameter is always going to be the same. I don't mean the height and the diameter are always equal. I mean that as the pile grows or shrinks, the ratio between the two is the same. So maybe for very, very fine sand, that ratio between the height and the diameter might be 0.4, which means the height is 0.4 as great as the diameter. It's quite a wide, short cone. But for something that's more coarse, that ratio might be different. That ratio might be 2 to 1. It might be twice as tall as it is wide. And that piece of information is in this question. It says the height of the pile is always 3/5 of the diameter of the base of the pile. That's an important piece of information. You cannot solve this problem without considering it. So what's happening here? We're pouring grain into this pile or onto this pile at a rate of 200 cubic feet per minute, which means the volume of the grain in the pile is increasing at 200, and it's cubic feet per minute. Okay, we just have to remember all our dimensions are feet and minutes. What is the rate at which the height is changing when the diameter is 32 feet? And it just occurred to me that today would have been an opportune time to give you a geometry formula sheet. And I will do so by the end of the class. I will photocopy it for you and give it to you. But the volume of a cone turns out to be 1/3 pi times the radius of the diameter squared times the height of the cone. And this is not a geometry course. We don't need to prove that. That's a fact. So the formula that we're going to be using will have to be this volume formula. And the question is, what is the rate at which the height is changing? Now, the classical approach, I'm just going to rewrite the formula without the word cone. The classical approach that you would see in most calculus textbooks is the following. Since dr dt is not in the list of rates that I want to find or that I know, I want an equation that doesn't have r in it. That's the classical approach, which is to say, let's get rid of the r. Because if I differentiate right now using the product rule, I'm going to get a dr dt somewhere. Because the derivative of the first will be 2/3 pi r dr dt. I don't know dr dt. So what you do is you scour the question and the information in the question in search of a relationship between the variable you want to keep, h, and the variable you want to eliminate, r. And it's there. The diameter, 3/5 of the diameter is the height. You've got to really think carefully about that. The height is means equals, 3/5 the diameter. But the diameter is 2 radii. I mean, I suppose I could have written height equals 3/5 diameter and then substituted in 2r for the diameter. But the bottom line is I now have a relationship. And now I have to rearrange that for the variable I want to eliminate. And again, I want to eliminate r because I don't have an r in the formula. So I rearrange this and I get r is equal to, let's see, 5/6 h. And I hope we can agree on that. Believe it or not, this is where people will mess up, even in a calculus class. They will rearrange that wrong, or they will read that highlighted statement and interpret it backwards or something. So the radius is 5/6 of the height, and what we're going to do now, this is not a difficult problem, we're going to take that and put it right there. Because that's what the radius is, and we will have accomplished eliminating the radius from the equation. So what does that give me? It gives me v equals 1/3 pi times that radius, which is 5/6 times the height, squared times the height. And all that's left is to simplify that, differentiate it, and answer the question. What do I get here? Volume is equal to 1/3 times 5 squared, 25 over 36. I want to say 25 over 108. So I'm asking you to extract all of those numbers and see if that's what you get. I mean, the 5 squared is 25. I'm just asking you to confirm if 3 times 6 squared is 108. And I'm pretty sure it is. So we get that times pi times h cubed, and we're off and running. So we've developed a formula for the volume of a cone using only the height under the circumstances where 3/5 of the diameter is the height. This isn't always good for every cone. Now I can differentiate, so dv dt equals, I'm swinging that 3 down in front. Given that 108 was 3 times 36, when I cancel that 3 with the 3, I'm left with the 36. Pi h squared dh dt. The question was, what is the rate at which the height is changing when the diameter is 32 feet? I mean, nothing's ever really easy. I mean, we have some work to do here on taking that diameter and finding the height, but not a lot of work. Because didn't the question say the height is 3/5 the diameter? Well, the height then is 3/5 times 32. And again, we want to use exact values, at least until the end. I believe that's 96 over 5. Okay. Correct me if I'm wrong because I've scrolled it off the screen, but I believe dv dt was 200. Okay. 25/36 pi 96 fifths squared dh dt. And now we just have to play around with the numbers. Over 5 squared is 25, which cancels with that 25. You can deal with the numbers however you want. I'm just talking my way through them. 96 over 36 is 49 over 18. I don't think that simplifies any further. So I have 200. I have times the 36, and I have divided by 96 squared, right? That's a nice fraction. 25/32, and it will be over pi. So I just want to double check. I've taken 200 times the 36. I've divided by the 96 squared, and I've divided by the pi. And I didn't worry about the 25 because this 25 over this 5 squared will be 1. So this is what I'm getting for dH dt. Seeing no objection, let's just move forward with that. Oops. This is a change in the height, so this is feet per, was it 200? It couldn't have been 200 cubic feet per minute, was it? Wow, that's really coming out quick. And that's dH dt, and if we want to find out what it is as a numerical decimal approximation, then we can figure it out. Of course, do not do this, right? That's not 25 divided by 32 pi. That's 25 divided by 32 pi. Approximately 0.25, about a quarter of a foot per minute. So any questions with that example? Okay, now could you have taken a different approach? I want to show this approach to you and then tell you why I think it's not a good approach. But you could have said, where's 5/6 stage? I'm gonna differentiate this anyway, even though I don't know dr dt. So I get dv dt equals, I have to use the product rule where this is the multiplication, the derivative of the first times the second plus the first times the derivative of the second. Are you with me on that product rule application there? And then somewhere along the way, we said that R is 5/6 h. And I've seen people do a question like this way, and I don't like it. I'm taking the same approach that I did with Christian's question about the rectangle, where I had that second strategy. That's what I'm doing. But the problem is with this particular strategy, here's what happens. I get dr dt equals 5/6 dH dt, and it isn't a dead end by any means. It's just that the problem with doing it this way is you don't know dr dt. Well, what you're going to do is you're going to put this here. But even as you start to walk down this road, I think you see it's more trouble than it's worth. That product rule really makes things more complicated to work with. But that will work. Then again, not only do you have to figure out what the height is to proceed from here, you have to know what the radius is. That's not a big deal, because if the diameter is 32, the radius is 16. Anyway, there's a lot more little pieces you have to do to make it work this way. All right? The next example is going to reveal to you that although there might be two strategies for many of these problems, and what I'm going to call strategy 2 is sometimes easier for you, but strategy 1 is easier in this example, just coming up with one formula. Sometimes you have to make a decision as to what's easiest. So let's take a look at the next question. And rather than asking what is the rate of change of the radius of the snowball when the volume is 240 cubic centimeters, let's find out what the rate of change of the surface area is. Why? Why not? And I'm challenging us here because finding a formula connecting volume and radius is easy. Finding a formula connecting surface area and radius is easy. Finding a formula connecting area and volume is not easy. So the first thing, I mean, I hope we understand what's happening here. We have an ideal situation, idealistic anyway, where you have a snowball and it's melting and it's maintaining its perfectly spherical shape, which means the volume is changing and the surface area is changing. If you're told the volume or the snowball is melting at a rate of 24 cubic centimeters per minute, then dV dt, pardon me, dV dt is negative 24, right? The rate of change of the volume is negative because it's melting. We have to understand the English language a bit. And we have to find dA dt. The best solution to this approach is beautiful. I mean that in the sense of the word beautiful. It's elegant. A beautiful or elegant solution in math is one where if you go down that road, they almost hand you the answer when you look at it the right way. But you have to find that solution. So let me give you the formulas for volume and surface area of a sphere. The formula for volume is 4/3 pi r cubed. And again, I will give you a formula sheet today that's a geometry formula sheet for two-dimensional figures, which will be area and perimeter and stuff like that, and three-dimensional figures, which would be surface area and volume. The surface area of a sphere is 4 pi r squared. So let me now show you, and I don't know if you want to write this down or not, because I don't even know that I will complete the problem this way. I might. We have time. We're not. We'll see. See, the problem is, from the classical standpoint, dr dt is not in this list. So what we would want to do is get a single equation relating area and volume, in this case, that has no radius in it. So what you would need to do is rearrange one of these for r and substitute into the other. R squared equals a over 4 pi, which means r equals root a over 2 root pi. Because the square root of a is root a, the square root of 4 is 2, the square root of pi is root pi. And this is r. So if I look at my formula for volume, it's 4/3 pi r cubed. And I mean, I think you see where this is going. It's just going to be a bit of a pain to deal with. Well, I'm going to write this with exponents in the next step. But I have to put that in here. So I have to cube everything here. Let me just write off on the side so that we know and I don't have to write it a second time. These are the same. So I have to cube this thing when I put it into the volume formula, which means my volume will be 4/3 times pi times a to the 3/2, because I have to cube a to the half, over 8, because I have to cube 2, and over pi to the 3/2. Which, I mean, if you're good with exponents, this isn't that tough. But again, the elegant approach that I literally just stumbled on one many years ago, one time when I was doing this, I tried something different, and it was a very simple approach, and we'll get to that. So I can clean this up, certainly would want to clean this up. I think it's that. 4 over 3 over 8. 4 over 8 is 1 over 2. 1/2 times 1/3 is 1/6. I have a pi to the 1 over a pi to the 1.5, so a pi to the 1 cancels on the top and the bottom, and that's what I have. And I chose to write it this way. I'm going to write it a little bigger. I chose to write it this way just to impress on you that this thing is a coefficient. So the differentiation and the conclusion to the problem is not difficult here. It's just all those goofy exponents. My derivative, so I guess I am going to complete this. Well, we'll continue walking down this path. Will be 3/2 times 1 over 6 pi to the half. And you know, figuring out what 1 over 6 times 3/2 is nothing I want to waste my time with. Who cares what it is? When we need to calculate it, we will. And then I have a to the 1/2, and then I have dA dt. So I move the exponent down in front. My new coefficient is this whole thing from here to here. The base remains the same, but I drop 1 from the exponent, and then I multiply by dA dt. Now it's time to pump numbers in there and get an answer to the question. What were we told? Oh, my goodness. When the volume is 240, well, I don't have a volume in there. I do have an A in there. So here's where I'm probably going to, and I will, decide I don't want to even continue down this path. If you want to pursue the end of this approach, you can. But what you need to do is take that 240, we'll do it here. Solve this for A so that you can put A down here. Oh, right away, my brain is weary at this point. Like I'm losing interest, really, is the best way to describe it. As a student, I'm probably going, let me take a look at the next question. But I think with what one of my teachers in high school called stick-to-itiveness, you could finish the problem this way. How many of you, though, understand that what I'm going to call the classical approach, which is to get a single equation to do the job, which is I'm going to call method 1, you recognize that at some point, probably halfway through this work, maybe there's a better way, or you hope there's a better way. Okay. Well, the better way is to just use both of those equations. Let me show that to you. And there's a better way, and then a better way, if that makes sense. So what you can do instead is differentiate each of these. So when I differentiate my volume formula with respect to time, I get dV dt equals 4 pi r squared dr dt. That's kind of interesting that the 4 pi r squared happens to be how you calculate surface area. I know that's not part of the solution to the problem. I'm just pointing it out to you. Okay? That the derivative of volume gives you area in this situation. And then when I do this, I get dA dt equals 8 pi r dr dt. So here is the not perfectly elegant approach, but pretty clever. That now you put the negative 24 here to calculate dr dt, to put dr dt there to calculate dA dt. That's pretty slick, isn't it? There's a downside that you need to find r. You need to put that 240 cubic feet, pardon me, cubic centimeters, in here to get r to proceed this way. We're not going to do that. You could, but you know, if you saw this question on an exam, if you did either the classical approach or you did this with all these arrows, it's eating up a lot of time. Does anybody have a better idea? And I'll give you a hint, the answer's on the board. Like the path we want to follow is on the board. I'll give you another hint. Somebody's got to have it.
Do you set them equal to each other?
The dRdt's? Yes, we could do that. We could rearrange this for dRdt and rearrange this for dRdt and set them equal to each other. There's an even slicker approach to get what we're after, and it's to divide both equations. I'm allowed to divide equations. I'm going to divide this and divide that. And what do I get? And sometimes the math gods smile on you. I get dv dt over dA dt is equal to r over 2. I mean, don't get me wrong, we still have to find the radius to answer the question. But maybe on an exam, the question would be given to you and it would say, instead of when the volume is something, it says when the radius is 10. And then you just go 10 divided by 2 and, you know, do your cross multiplication. So what this becomes is 2 dv dt equals r dA dt. So all we need to do to answer the question is find out what r is. And again, this is the level of math you're dealing with in this class. It's university level. There are all kinds of ways to do problems, and sometimes you come up with a very quick approach. And again, don't get me wrong, was the volume 240? Okay, we still have to solve this. But that's not a big deal, right? Take 240 times 3 divided by 4. I believe r is the cube root of 180 over pi. So I would like you to confirm that when you cube root, that when you take 240 times 3 divided by 4, you get 180. I'm sure you do, but yeah, over pi. Okay, what are we after, dA dt? So just put the numbers in. 2, negative 24 was dV dt. Is that the case? Equals r cube root of 180 over cube root of pi times dA dt, and solve for dA dt. Quite frankly, I'm not interested here in whether the cube root of 180 simplifies because it contains perfect cubes. I don't care. Okay. If you're looking for an exact value, somewhat simplified, it's negative 48 cube root pi over cube root 180. And I would like to do the last example with you today. So we will leave it there. That would be square centimeters per minute. And if you want to find out a decimal value there, you can. So right away, just an observation about related rates. When we first started this, and I told you, well, we'll probably spend 4 days on this. You looked at maybe that first lesson and went, 4 days on this? Things are picking up here, and it might even be 5. You know, the plan is to have tomorrow as the last day for related rates. We might continue this Monday if I feel it's valuable. But I want to move on and cover the last question, the slipping ladder question. So you have a ladder it's a very basic question. It's the kind of question that if you see on an exam, you should know exactly what to do and you should be done within a minute. So you have a ladder leaning against the wall and it starts to slide. I have learned from experience that the foot of a ladder can be very slippery under the right conditions. You know, there's also safety rules. I don't know if you know this. There's a ratio of the height of the ladder to the base, from the base of the ladder to the wall. The basic rule is if you put your feet on the foot of the ladder and you can hold the ladder like this, it's steep enough that it's probably not going to slip. I mean, if you're on a skating rink, you want to anchor it. But if you have to lean over from your feet to grab the ladder, it's not steep enough. It's not safe. Just life lesson, that's all. So what happens here is we have a wall and we have the ground or the floor, and we also have a ladder. And the ladder is leaning against the wall. So what happens is it starts to slide. And it says that the foot of the ladder is moving away from the wall at 1.5 feet per second. Something looks awkward about how this is spaced. Does yours say 1.5 feet per second? Okay. So this distance here, everyone, is changing. Well, then we need to call it a variable. Why don't we call it x? So then dx dt is 1.5. Feet per second. The question is, how fast is the top of the ladder moving down? The question is, how fast is this point moving down towards the floor at a particular point in time? Well, that means that this distance is changing. And if we know the rate at which that distance is changing, we know the rate at which that green dot is moving. So we need to call that something, and I'm going to call it y. So dy dt is what we are after. Now, we need a formula relating x and y. Any ideas? Greg?
X squared plus y squared equals 12 squared.
Equals the hypotenuse squared, right? Yep. I'm going to ask a question that is, it's almost so simple it might be tricky. Why are we allowed to put 12 in there? I thought you weren't allowed to put numbers in for variables until after you differentiate. Like the Pythagorean theorem is x squared plus y squared equals z squared, let's call it. Why are we allowed to put z equals 12 in at this point?
Because 12 is constant.
Right, because 12 is constant. Now, if this were an extension ladder, and as it's slipping, it's also collapsing, you'd be in a terrifying position, but then you would have to leave the 12 out because it's not constant. Anyway, pretty basic question. Differentiate. 2x dx dt, just differentiating with respect to time, plus 2y dy dt equals nothing. And we can solve the problem. The 2's cancel, so x dx dt equals, let's go plus y dy dt equals 0. What do we know? We have to be told some conditions here when the foot of the ladder is 3 feet. So what I'm you know me, I'm sometimes pretty picky, overly picky. This diagram is a diagram for every point in time, right? That's what you use to develop the formula. When I put this 3 here, it's no longer for any point. I'm just using the diagram to help me answer the question. You know, this is 12. If this is 3, it should be pretty easy for you to calculate the missing side using the Pythagorean theorem. It's 12 squared minus 3 squared, which is 135, I think. Can you confirm? 135. So this y at this point in time is root 135. Put the numbers in. 3, 1.5, root 135, dy dt. Equals 0. So negative 4.5 is what I get here. Well, I get 4.5. I subtract this over and divide by root 135. That's the answer to the question. Well, I shouldn't say that's the answer to the question. This is what dy dt is. To be pedantic, which means really picky, that is not the rate at which the top of the ladder is moving down. The rate at which the top of the ladder is moving down is 0.387 feet per second. You wouldn't say it's moving down at a negative rate. That's a double negative. That's being, as I said, very picky. So the top of the ladder at that instant will be moving down at about 0.4 feet per second. And by the way, this intuitively makes sense. When the ladder is like this, and the top of the ladder is very close to the ground, the top is moving down really fast. Really, really fast. Even if the base is still moving at 1.5 feet per second. So that's where we're at now with related rates. Continued addition to problems that you should know how to do. In your textbook 6, 7, 8, 11, and 17 on page 145, I'm curious about what number 10 is. Right, don't worry about number 10. We will tackle that tomorrow. There are a couple more examples we want to look at tomorrow. I'm really inclined to say we're probably going to finish with examples and learning tomorrow, and then maybe Monday will be a practice day. Something. I don't think we're going to move on Monday. We don't need to. Is it the case, be honest with me, that you probably did not, that there are people in the room who didn't do every single question from yesterday? Okay, I mean, if you have to be, I want you to be honest. You have to go back and try those too. You have to know how to do these.